All right. Now, the interesting thing is this is going to be recording the behind-the-scenes kind of stuff going on here. So it's actually not going to look exactly like this. This is a periodic table of elements. It's a lovely periodic table of elements. One of the cool things about the periodic table is that it represents everything in the universe that makes everything. Stop for a moment, think about that. Anything that can exist, does exist, is made from only the things on this periodic table. Cells, DNA, human beings, the miracle of life, okay? Air, weather, our planet, the stars, everything that is or ever will be is made from these elements. And what's even cooler is that only 90 of them are actually natural, which means that most everything that is natural only is represented by 90 of them. You yourselves, you are only made of 6 of these elements. 6 of these elements constitutes $43 worth of material I can buy in a hardware store that makes Colby. Okay?
So I'm worth $43.
You're worth about $43.
Ow!
Okay?
Plus the extra stuffing.
Drake's worth about 50% that. He's a really reasonable $25.99. On sale today.
Buy one, get one free. Half off.
Buy one, get one free, half off. Yeah. You guys are made of only 6 elements. You'll learn more about this at the end of the week. That's what that video that I want you to watch at the end of the week is all about. It's about these elements, what makes you, where they come from, like that. All right, let's go ahead and get started here. Nitrogen, helium, chlorine, mercury, sodium, these are elements. They have unique names. Okay, we find all of these on the periodic table. These are just some special ones that are like, for instance, neodymium. You may never have heard of neodymium, but that little element right there is what makes Beats headphones one of the top headphones in the country. Because the magnets needed to make good music, good speakers, come from neodymium. Okay, so that's really important if you like good headphones and audio equipment. Helium, we know about helium, but helium, believe it or not, is something that exists in our atmosphere. We have to pull it out to put it in cans so we can make balloons inflate, all right, and other things like that. All right, if you recall, Aristotle was the first to start to theorize that there are these kind of elements that make up everything. Now, we know that his idea of the elements was totally wrong. He hypothesized air, fire, water, and earth, and, well, we know that's just not it. Okay? There is a really old show, and I say old, when I was a kid. Well, Avatar takes this. Yeah, that's good. Like the Airbender. But there's actually an even cheesier one. You got to look this up on YouTube. It's just a classic, right? You what? No, I'm not going to. I don't have time. But it's called Captain Planet. Okay, if you've ever seen Captain Planet, they kind of have these rings of power that, you know, they can control the air, fire, water, and earth. It's really, it's just as cheesy as it gets. Yeah. So anyway, check it out. That was a show that I loved as a kid. Loved it. I watched it all the time. Go, go, Captain Planet. Okay, you just gotta look it up. Okay? Science has come a long way. We now know that there are not 4 natural elements. There are 90 natural elements. Okay, write this down in your notes. They are elements numbers 1 through 92. That's not on the slide. Okay? But what does not add up here? Elements 1 through 92 are natural. I said how many are natural? Yeah. 90. That means there are 2 in there that are not. And you can tell which ones they are by looking at the periodic table. All of the solid letters, okay, on a periodic table are natural elements. But look at 43. You can see it on that periodic table over there. It kind of sticks out like a sore thumb. 43 is called synthetic, means man-made. It does not occur naturally. 42 and 44 do, but 43 does not. Okay? That's a man-made element, so it's not naturally occurring. All right? I wanted you to write down the elements 1 through 92 are naturally occurring elements, with the exception of 43 and 61, promethium. You'll notice it also sticks out like kind of like a sore thumb down here. Promethium, PM, also is man-made. Okay, so there are 90 elements that make up the known universe. This is incredible. 90 elements can make up all of the different life and things that we can make and see. And what's crazy about this is we combine these elements in different combinations and we come up with new stuff every day. For instance, the same thing, the same substances that make diamonds, make your pencil lead, and make plastic. They have the same elements in them. And yet, just the way we use them makes their purpose totally different. That's fascinating to me. Mackenzie. They are natural, yeah. Except for 43 and 61. And you can see those because they stick out. 28 others, including 43 and 61, 28 elements are man-made. All right, you don't have to write down each slide because I'm going to give you all of these slides. You need to write down the underlying things. Okay, so I'm going to move on. The elements alone or in combinations make up our bodies, our world, our sun, and in fact the entire universe. To give you an idea of how big our universe is, okay, this is a picture of the Milky Way galaxy. And that square right there, okay, constitutes the region or location in the Milky Way galaxy where our solar system is located. And if I were to actually try to find our solar system in this galaxy, it would be smaller than the tip of a pin. Our whole solar system, which takes us 40 or 50 years to cross, going at about 18,000 miles an hour, would be no bigger than maybe a pin tip on this picture. Okay, so we're talking about a vast and numerous universe. When you guys look into the sky, okay, when you look into the sky at night, most everything you see is just our galaxy. There is billions of galaxies. So take what you see in the sky, multiply it by billions, and that'll only give you a hint at how vast the universe is. Okay? All right. Now, to get back to more along the lines of our reality, the Earth. The Earth and its crust is made mostly of oxygen. It's crazy, right? We breathe the stuff. But that oxygen, and not just oxygen, is combined with silicon, okay, and that makes up a majority of the rock on the face of the Earth. How many of you have ever heard of quartz? Quartz? How about mica? Feldspar? Okay, granite? Okay, feldspar and mica are minerals that are made mostly of silica. Igneous rocks have a high concentration of silica, like obsidian. There's a good portion of it also in like pumice and other pyroclastic rocks. Okay, granite has got a high concentration of quartz and mica and feldspar in it, especially pink granite. Okay, a very common type of granite. Okay, so silica is primarily 1 part silicon, 2 parts oxygen. Okay, that's silica. Silica makes up a large portion of the rock of the Earth. Our mountains, our sand, okay, magma, volcanoes, they are made of this stuff. Oxygen and silicon. Now, you'll notice that the third most abundant element in our crust is aluminum. But if you tried to go into your backyard and say, hey, 8% of the Earth's crust is aluminum, it's got to be everywhere. So you go in the backyard and you start digging, you will never find it. Because aluminum atoms are in the soil, but those atoms are not bonded to make aluminum foil or aluminum like on a beautiful MacBook, okay? That aluminum is in dirt, brown reddish dirt, and a majority of it that can be mined out of the Earth is in Australia. So that's where we get it. Most of our aluminum comes from Australia. Iron, it makes up a very large portion of our crust. How many of you have ever eaten Raisin Bran? Okay, do you have Raisin Bran at home, anybody? Okay, I do. Okay, you take the Raisin Bran flakes, not the raisins, but the flakes, and grind them into a powder in the bottom of your bowl. Then take a magnet and put it over the bottom of your bowl. It'll pull the iron right out of the bran flakes. Okay?
Isn't that a bad thing?
Not necessarily. Your body needs iron. It's in your cereal. You can look on the back of the box. It tells you there's iron in this. You can pull it out of your cereal. Okay? So, iron constitutes about 5% of the crust. If you've ever seen really red ground, like especially through the hills of Kentucky and Tennessee, that's a lot of iron in the ground. Rust is iron, okay? So it's great stuff. Calcium, sodium, potassium, magnesium, especially sodium and potassium, those are absolutely necessary in your bottle. It is. You don't want to eat rust because it's not in the right format. Rust is actually bonded with oxygen. And when iron and oxygen get together, it makes a nasty mess. You eat your cars, nails, the rest of it. All right, then there's titanium. Believe it or not, there's a fair amount of titanium. And hydrogen. This is 10 elements. There are 80 more found in the earth. 80 more, less than 0.1%. A lot of elements, especially the ones at the bottom of the periodic table, Mr. Hogel, are rare. Very rare. So rare, in fact, that there's only just 1 or 2 places in the entire earth where they can be mined out of the ground. And a lot of it comes from our neighbors across the Pacific, China. They have special, you could say, mining operations that pull these rare metals out of the earth. And because they're so rare, they have to go through tons of material to pull out just a tiny little bit, which is why Beats headphones, which have neodymium in them, neodymium is a rare earth metal, are expensive because you have to move mountains, literally mountains of dirt to get just a little bit out, okay? So this is our earth, and it's made up primarily of 10 elements. There are 90, however, that can be found. You just have to know where to look and how to get them out. Questions? Any questions? Questions about the periodic table? That's awesome. Elena? Can you recreate them? In theory, if we wanted to, we could try to create elements. Sure. It's easier to find them. The problem with creating elements or recreating elements is that it takes an incredible amount of energy. And oftentimes, it's not financially worth it. Okay? Most science, and I'm not going to say all, but a lot of science is financially driven, right? If it's not going to better mankind or be profitable, scientists are going to have a hard time undertaking that venture. So most everything that scientists are doing, a lot of them, is funded by people who have an interest in making money off the process. Okay? So that's the disadvantage, right? There's a lot of things we could explore, but we don't because there's no profit in it, at least right now. Chloe. Well, see, we don't know how much of space actually has these elements, which is why recently, like for instance, the Japanese space program landed a probe on a meteorite. And they're taking samples of the meteorite to see what it's made out of. That's very cool. Okay? And then that meteorite or that probe will come back to Earth and deliver the samples, and we'll be able to analyze those samples. All right, the periodic table. It organizes the elements in a very particular way. There is a reason this crazy looking table has got all kinds of notches, corners, dips, dives, and the like, okay? For instance, it's not just a big square, it's not just a big list. It's got high points, like on the left and the right. It's got dips in the middle. It's got breakout boxes, okay? It's got all kinds of crazy stuff going on. There's a rhyme and reason to the madness. Rhyme and reason, okay? When the periodic table was first invented by the Russian Dmitry Mendeleev, which you'll learn about, he looked at the properties of these elements and he said, hey, there's patterns here. For instance, look at the first column, lithium, sodium, potassium. He said, wow, these 3 elements are very similar. When they touch water, they explode. Yeah, that's very similar. Nothing else does that. That must mean that they have similar chemical properties. The underlined word here is chemical. But that's not all. Beryllium, magnesium, calcium, strontium. Well, these are all white powders. That's weird. And they all have very similar chemical properties as well. Hey, all of these elements elements on the right-hand side, they don't do anything. Helium, neon, argon, krypton. It's like they don't exist. They just float there. They don't do anything. That must mean that they kind of have a similar thing going on. And he noticed these things. And he started to put them together. Not just him, scientists, people who were exploring elements, at least the ones at the time, said, there's weird coincidental things happening here. Okay? And so what they did is they made little groups, and they started to try to put the pieces together. What they found was that there was a repeating pattern. Okay? Physical and chemical properties. Don't write it all down. Just write down the word chemical. I'm going to give you this. Okay? I already said that. I want you to pay attention to me because this is the key idea where this came from. It's not just a table. It was actually created out of observation, just like everything else in science. Dimitri said, hey, I go across the periodic table and I know that they have certain masses, okay? I know that hydrogen's really small, helium's really small. But every time I go across and I get to an element that doesn't do anything, a pattern repeats itself. So then I go over here and I start counting up the elements I know that are getting bigger and bigger, and I get to an element that doesn't do anything, neon. And then the pattern repeats itself. And so he started to play around with the pattern. He started to line the elements up. And this is the table that took shape. This one right here. Literally on scrap paper, they have evidence to suggest that Mendeleev literally for years sat at a table and was playing with these elements and came up with this pattern that is the periodic table. And so we call it the periodic. Periodic means to repeat. All right, I periodically go to the store to get groceries. Well, that means that I go on a regular pattern to the grocery store every week to get groceries. You periodically come to class. That means that every day at the same time you come to class. It's a pattern. The periodic table, the pattern table of elements. That's what it means. There's a pattern that's being followed in this table. I could make the non-periodic table of elements and just randomly distribute them all over the place. Okay? It'd be the non-repeating pattern table of elements, which would be kind of cool, just saying. We could call it the Bornheimer table of elements. It would look like that. Just good. Yeah, all right. So if you understand the organization of the periodic table, you start to see that a lot of things fall into place. Okay? A lot of things. There are 20 to 30 different patterns that resulted in this organization. I can't even begin to unpack them because some of them are too advanced. Okay, but as you get through chemistry, you will unpack all of them. You will unpack the size of atoms and how they absorb and release energy and how they play with or mix up with other elements based on their position in the periodic table, etc. Okay, so that's the periodic table. The first thing we have to do in understanding it is we have to be able to read it. Okay? H. What element? Hydrogen. Incredibly abundant. It's not the most abundant element on Earth. It is the most abundant element in our universe. Why? What is a supermassive that's made of hydrogen? Say it louder. The sun, the stars. Our sun is made of hydrogen. Okay? All suns are made of hydrogen. That's what makes them bright. They're undergoing nuclear reactions. So what's happening is in our sun, hydrogens are hitting each other and fusing together and releasing huge quantities of energy. So what's actually happening in our sun is it's taking hydrogen and turning it into helium. And as a result, all of the energy is being released. Okay, and there's enough hydrogen to let this happen for billions of years. Huh? Yeah. In theory, I guess you could say that if you went close enough and survived it, that yeah, maybe your voice would go really high. Oh, it's the sun! Yay! It's so bright and beautiful. It's a little warm. Okay? So, needless to say, yes, that's kind of what we got going on. All right, so hydrogen. All right? Hydrogen is, we can characterize it by the big symbol on the front of each element. However, not every element is as blatantly obvious as hydrogen. For instance, tungsten. Okay, if you were to look for tungsten on the periodic table, which letter would you think you'd be looking for? T. Yeah, everyone thinks T or TU or tongue. Okay, or TG or something. Nope, it's W. Right there, tungsten. W, dubs, W, okay? Right there, W. It's W. What? Okay, how about gold and silver? Yeah, AU, AG, what? Okay, lead, PB, plumbum? Yes, plumbum. All right, tin, stannous, what? Iron, ferrous, what? Copper, cuprous, what? These are Latin words. Latin. Potassium, yes, potassium, K. K? K? Yes. Copper. The Kappas see you. The Kappas, woo woo. The Kappas, they're coming for you. The Kappas, they see you. The Kappas, they see you. The Kappas see you. The Kappas see you. The Kappas see you. Okay? So, yes, these words came from Latin. They came from Latin. And yes, we still use them today because it makes sense because we've used them for so long. They are ingrained in the scientific community. Okay? Plus, we can't really just change them that easily. For instance, T is pretty common on the periodic table. Okay? We have TH and TM and TE and TL and TC and TA and TI. So throw another T in there with tungsten. Ooh. But W is not very common, okay? W. Tungsten. Okay? No. No straight T's. Well, because. TB, but no. No T. So, the letter indicates the name or symbol of the atom. The big number, which is different on every periodic table, they don't all look like this. The big number tells us which particle. Yeah, protons. Excellent. There are no two elements that have the same number of protons. The little decimal number tells us the mass of one atom of that element. Okay? And I'll tell you right now, it's actually an average. They took all the isotopes of hydrogen. Okay, so let's say I cloned Gretchen Rainey. But then the clones of Gretchen Rainey all had different subs for lunch, okay? One had an Italian sub, one had a 6-inch Subway melt, another one had the full meatball marinara sub, just the whole 18 inches. It was a super long one, okay? So we've got 3 Gretchen Raineys, okay? They're all Gretchen, but, okay, they're all going to weigh just a little bit different because one had a normal sub, one had a tiny sub, and one had the full meatball marinara 18-inch extra long booyah, okay, sub. So, how do we represent Gretchen Rainey? We averaged it. We take this one, add it, divide by 3. Okay, now it's more complicated than that, mind you, but that's the basic gist. So we know hydrogen, there are isotopes, different versions. There are 3 of them, protium, deuterium, tritium for hydrogen. So what do? They kind of average it out. And they say this mass right here, the 1.000794, is an average of all the hydrogen in the universe. Okay? And they're pretty good. They modify this number every so often as they get more data. But it hasn't been modified in a while. All right. Yeah, this blank here is 1 proton. What's in a square? Well, we've already kind of talked about it. The atomic number, the symbol, the mass, and oftentimes what that element looks like at room temperature. This, ladies and gentlemen, is room temperature, 22 to 24 degrees Celsius, or here in America, 68 to 72 degrees Fahrenheit. Okay, that's room temperature. That's what makes us feel cozy. Okay, all of us are a little different, but for the most part, this is room temperature. So if I were to bring any element into this room, I can tell you what state of matter it's in, solid, liquid, gas, based on the temperature. Look at this periodic table over here behind Colby. You see a lot of it's red. Red means that if I brought it into this room, it'd be solid. It'd be a powder or a hard rock. The blue ones, there's only 2 of them, mercury and bromine. Those would be liquid. Okay, so if I brought them into this room, they'd be liquid. Both are pretty dangerous, by the way. The green ones are gases. Okay, so if most of them are in this room right now. Oxygen is in this room as a gas. Thank the Lord, at room temperature, oxygen is a gas. Okay, if it was a liquid, we'd be in big trouble. Okay, because then we wouldn't be able to breathe it. So we'd all suffocate.
Well, divers use liquid oxygen if they're going super deep.
But as it comes up through their respirator, it turns into a gas. They can just put more of it in the tank as a liquid. So it's converted between liquid and gas as it comes into their respirator. All right, so you have all of this information that we can get on the periodic table as well. This one too, the solid letters are solids. These outlined ones are synthetic, man-made. Blue, liquid. The red ones are gases. That includes hydrogen, which is all by its lonesome. All right, this Bohr model of the atom, Bohr, boring student since 1913. This is his hydrogen atom, nucleus, electron, not to scale. Okay, but the atomic number tells us the number of protons. Hydrogen has how many protons? Mackenzie Berg, help me out here. Protons, hydrogen. Yes, thank you. Whew. Okay, boron. Look it up on the periodic table, right here. How many protons?
6.
Oh, close.
5.
5. Carbon has 6. Uranium. Anyone? Uranium has how many protons? No. 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 92. 92 and approximately 140 neutrons. Okay, it's a massive element, the largest naturally occurring element on Earth. It's massive. All right, now atomic mass. This is the mass, not to be confused with atomic number. That's the protons. Atomic mass is the mass. This number right here is crucial for pharmacists. It's crucial for engineers. It's crucial for scientists. It's crucial for anyone that makes anything. And the reason is in order to chemically combine materials, which happens in a number of facilities every day across America, they have to understand the nature of one single atom. Not kidding. So for instance, I want to make nylon. Nylon is the combination of two chemicals they put into a vat as a liquid, and then when it comes in contact with air, it turns into rope. Okay, it turns into string. So literally what they do is they have this big boiling kettle of a liquid, they dip something in it, and as they pull it out, it turns into nylon string. And then they start to just pull it out, and they make piles and piles of nylon, and then they weave it into rope, and that's what you buy in the store. Well, how do they get the mixture right? They have to know what the atoms of those chemicals are like. They have to know how those atoms are going to come together and bond. They have to know how much to use so the mixture is just right. It all comes back to the atomic mass. There's actually a special field of chemistry called stoichiometry. Literally, that's what it's called, where they actually can do the calculations to make this happen. So this right here is helium. How do I know? How do I know this is helium? Yeah. I can look at its atomic. Yes. And it tells me the number of. Yes, and it has 2. The red ones. Okay. How do we know that? Because they're color coded.
How do we know the color?
Because the red, when we're talking, great question, Millie. The red, when we're looking at the periodic table, okay, the red when we look at the periodic table, over there is solid, here is gas, but this we're looking at the particles in an atom. Protons, neutrons, electrons. Okay? The atomic mass of helium is 4, approximately, because a proton has a mass of 1. And we're going to talk about the units in just a minute. Chloe. For our purposes, absolutely, yes. Protons are almost all the same size, neutrons all the same size, electrons, but they're not the same size as each other. Okay? Protons and neutrons are very close but slightly different, and electrons are way smaller. Okay? Almost not even calculable. In mass, yes. Here, I'll give you a good example. This is the AMU, okay? Or actually the AMU. Don't say AMU when you get to high school because their teachers are going to look at you weird. Okay, the AMU, as I like to call it because it's fun to say, AMU, dear AMU. Okay, the AMU is the atomic mass unit. unit?
Hi.
Hi. It is the measurement of one proton, and it's how we calculate the mass of atoms. One proton, here on the left, equals 1 AMU, or atomic mass unit, on the right. So if something had 2 protons, it'd have 2 AMU. If it had 3 protons, 3 AMU. If it had 4 protons, 4 AMU. Okay? So the AMU, or AMU, is equal to the mass of 1 proton. So when you're looking at an element on the periodic table, and you see its atomic mass, that kind of gives us insights as to how many protons it has and what the mass could be. The atomic mass unit. If something has 6 protons, like carbon, that's 6 AMU, but then also its neutrons are about 1 AMU too. So we've got all kinds of AMU happening here. Carbon has a mass of 12. It has 6 protons. So if it's 12 and it has 6 protons, that means it has about 6 neutrons in it. Okay, I have up here a bathroom scale. No, I am. No. Okay, the point I'm going to try to make here is this. When scientists weigh atoms, because they do, okay, when they weigh it, the nucleus would be me. Okay? I didn't max it out, did I? No, 235 pounds, 240 pounds. Okay? That's how much I weigh. All right, so when I'm looking at mass, that's a lot, right? And so I would represent the nucleus. The mass of the electrons would be represented approximately by this paper clip. Do you think, scientists, that it makes a big difference in the measurement of the mass of the atom? Did it drop? Yeah, I figured that might happen. Oh, really? That's awesome. Yeah. Hey, there it is. Okay. Oh, string 2. All right, so this would represent the mass of the electrons. It's so, no, this is not going to be sensitive enough. So ultimately, do the electrons play a large role in the mass of an atom? No, not really. It's mostly the nucleus. Okay, so that's primarily where it comes from.